blame.
Okay. Okay, so the last speaker of the day is Alessandro Sfondrini, telling us about exact results for the string worldsheet.
Okay, thank you very much for accommodating my talk in an already very packed program, and I apologize if I cannot take part in this very interesting program as much as I would like. First of all, I had some very strict constraints because of teaching, so I will only be here today and tomorrow morning. And second of all, I had the worst food poisoning of the last so many years this morning. So thankfully, Didina had a trick to make my stomach a bit better. So now I think I should be fine to give the talk. If I do succeed in giving this talk, it will be the first talk of the program sponsored by the Coca-Cola company. Okay. So because I think it's been a long day for most of you, I think I will give a Blackboard talk, which should be a little bit more interactive and hopefully the chance for you to stop me at any time if you have any questions. I'm perfectly happy to explain something in more detail or to at least try to give some more background. And speaking of background, this talk is about integrability, but in the context of string theory. And I realized that maybe not everybody in the audience is very familiar with this. Of course, there are some very great experts in the audience. So I apologize to the experts because I want to give at least a little bit of an introduction on the motivation that hopefully could be interesting for the other colleagues. So what I want to tell you about is how we can use integrability to compute certain observables in string theory and why it is important. So let's start from why it is important. It turns out that even in string perturbation theory, so even in the most vanilla formulation of string theory, where you're happy just to study a string, a closed string, like this circle here, let's call sigma the spatial direction of the string that propagates freely in some fixed background. Along some time tau. Even when you want to study these perturbations around this picture where you have higher genus corrections, this is actually something almost impossible in all but the very simplest backgrounds. And this is just the simplest thing, the propagation of the string. You have, of course, many more corrections, and you have more complicated dynamics that you can have. For instance, you can have string interaction by which two strings merge, which also come with their own corrections. So, except for very simple backgrounds, this is extremely hard. Backgrounds in which the string propagates. And because it is hard, there are many important questions that we cannot answer. So string theory is the best working theory of quantum gravity, even with all these difficulties, apart from maybe very low dimension where you can do other things. But in general, is our best shot at understanding quantum gravity, our best shot at understanding, for instance, the holographic principle in quantum gravity, the black hole entropy, for instance, and how it evolves, and we can understand very little if we cannot do calculations. So my proposal to solve this problem is to use integrability. Which immediately sounds completely wrong, because integrability is the most spatial thing that you can think of. Normally, it requires a very delicate balance. And I'm saying, well, you know, I can only work for very special things, but integrability will work much more in general. That sounds strange. So in order to convince you of why this is important and why this makes sense, I have to say a bit more what this word generic means. Yes? Backgrounds, BGD, backgrounds. Sorry. Yeah, sorry. Yeah, backgrounds, wanted to be that word. Any questions? So what's a generic background and what is a non-generic background? So when the, again, BGD background has only what are called NSNS fields, which have certain boundary conditions on the worldsheet of the string, then we get a local CFT in 2 dimension, or 1 + 1 dimension, on the worldsheet. So this is the case which is manageable, and it is the case of flat space and of a handful of other backgrounds. And when that is not the case, if there are Ramon fields or field strengths in particular, this is not possible anymore. And I don't want to write down an action for you and tell you which fields are Ramon, which fields are NSNS, but I just want to tell you that if you take any supergravity background in which the string can propagate, and that maybe it's interesting physically because of holography or because of black hole physics, generically it will have Ramon backgrounds, and you will not be able to use the CFT description on the worldsheet. But you will be able to use, in many cases, integrability. The backgrounds give rise to integrable models. In particular, at the very least, to classically integrable nonlinear sigma models, or super nonlinear sigma models, because you have bosons and fermions. And it's really many cases, meaning that not only there are many interesting backgrounds, but these backgrounds come in very large parametric families. So families with 1, 2, 3 parameters, and then you can construct many integrable deformations that break some of the manifest symmetries of the background, so give you something that geometrically looks like it has very little symmetry, squashed in many ways, but is still an integrable string background. Of course, this is not very different from considering squashing of certain nonlinear sigma models, but it's very intriguing that you can do this, preserve integrability, and preserve the fact that these geometries are string backgrounds. So, in this talk, I want to give you a flavor of how this happens, but I will only talk about the very simplest observable, which is this one. The integrability techniques apply to these corrections, apply to this pair of pans topology, they apply to much more general stuff. But for reason of time and concreteness, let me talk about this thing, where the nonlinear sigma model is in some finite volume, and I want to study it with integrability. The other thing on which I want to focus is one specific case. I don't want to talk completely in general, I want to write formulas, so let me pick one background, and I will pick, as it's written here, a background that involves anti-de Sitter in 3 dimensions. The reason why I want to do that is that this background is first important in string theory. In holography, many things have been understood there. It's important to the study of black hole physics and understanding the entropy of black holes in string theory. And it's also very important from the technical point of view of constructing an integrable model where we see very clearly the interplay between these NSNS fields and the Ramon ones. AdS3 is also very interesting because it's dual to a very interesting theory through holography, but it doesn't have that interplay. So because there is a bit less supersymmetry at the technical level in AdS3 than there is in AdS3, you can have more parameters, and you have, at the very least, a two-parameter family of integrable models. And the background, actually, to satisfy the supergravity equation and to be a critical string theory is not just AdS3, it's 10-dimensional. So there is anti-de Sitter space in 3 dimensions. There is a 3-sphere, and there is a 4-torus. Actually, there are several variations on the theme where you can put a K3 instead of the torus or something else, but let me just skip this. I just want to stick to the very simple, show you the very simplest. And as I said, this background is important physically. It has these SNS fields, and it can be realized just with SNS fields, but it also has Ramond-Ramond, and this gives 2 parameters. And of course, is integrable. Otherwise, I will not be discussing it. So let me tell you a little bit how these SNS and Ramond-Ramond appear. I told you there are 2 parameters, so just let me define them. So there is a parameter, one parameter is k, which is an integer, 0, 1, 2, and so on. And this is related to the strength of these NSNS fields. And the other parameter, I call it h, and this is a real number. And this is related to the Ramond-Ramond strength. So let me tell you qualitatively what happens to these backgrounds. So this is a 2-parameter family. And let me tell you the extreme case in which we have one and not the other. So if k is greater than 0, then on the worldsheet, we have a level k Versum-Witten model supersymmetrizes in some opportune way, and that describes the spectrum of this model, and also other things as well. So there is a very simple description as a field theory on the worldsheet, so in a sense as nice as a conformal field theory as you can get. And the spectrum, because of this, is known in closed form. Let me write how this looks like. So imagine that we have some state, which is a vacuum of this Versum-Witten model, which is maybe characterized by some parameter, which I call J. And then we just act freely with a bunch of oscillators that are related to the Versum-Witten model. Alpha minus N1, alpha minus Nm. And this thing has an energy which you can compute and looks something, I'm not being precise, of course, with the parameters and the normalizations and so on. It looks something like this. Where k is the level, and this curly n is just the sum over j of these mode numbers nj. So from this formula, you see that not only is very simple, not only is non-enclosed formula, but it's also enormously degenerate. This J is just something that characterizes the vacuum of the Vesumino-Witten model, and it has to do with some charge of some R symmetry. But I didn't want to go in this level of detail. It's just something that you will have to sum over in order to construct the whole spectrum. And there are bounds and there are details on which J's are allowed and so on, but yeah. More questions? No. That one thing that is missing is that actually these n's are defined to be positive in order to be creation operators. So this quantity here is all positive, if that is what was troubling you. So this somehow no, they come from different things. They have different stories. But let me, yeah. This is actually the same spectrum of free strings in lattice gauge, by the way. That's how also you get it. Yes. Thank you very much. That's the case in which only that one and the other one, crucially, is 0. Thank you very much, Jules. I apologize. So as I was saying, this is very degenerate. Enormously degenerate. And this degeneracy is not a geometric degeneracy due to the fact that you have SO3 invariance in the sphere, or SO4 invariance in the sphere, or whatever. It's just something very special of this model. If I now introduce, yes? Yeah, it's due to the fact that this is linearly constructed out of the representation theory of this Kac-Moody algebra. That is the reason, technically. But then the question is, what happens if you turn on a little bit of H, say? And what you see is that the spectrum becomes very hard to compute, but it's immediate to see, at least even at first order, that the degeneracy lifts completely. And also the form of the spectrum becomes very complicated and very involved. For instance, if we were to compute the spectrum of a given state, so we pick some particular choice here, and we have a certain spectrum H psi of a given state, it would look something like, maybe it starts out in an expansion in H, let's say. It starts out with some rational or integer number even. But then, if you were to compute it in some perturbative scheme, which is not important which scheme it is, it immediately starts spitting out non-algebraic numbers. So it's qualitatively a very different beast, this sort of spectrum. So this is an example. It's just an example of some state at k precisely equal to 0 and h greater than 0 in some scheme of perturbation. So this is just to tell you how different these two things are, but they are connected by a line of integrable theories. So the easy is the green one, k non-zero. It's a bit easier than the generic thing. Of course, the generic thing has everything, but it's qualitatively, it's very close to being as hard as the generic thing. I mean, there is not such a, you can see it from this structure, essentially, that these special things only happen here. And I will show you now how all this makes sense in the context of an associated integrable model, okay? Ah? Well, there are degeneracies, but not quite as many. In a sense, this is integrable, but it has an additional structure, which is a chiral structure, which we will see in a moment.
Sorry, if you specify the group of Vesumino, you also have a formula for J square, right?
Yeah. So this J square comes from the Casimir or whatever groups appear here. I didn't want to get into it, but is some certain supergroup, which is the symmetry supergroup of this background. I didn't want to get into that nitty-gritty, but you're absolutely right. More questions? Okay, now that I gave you this sort of overview and motivation, I will introduce the integrable model that comes out of this story. And if you're just interested in the integrable model, you don't like or you're not interested in string theory, you can just study that in its own right. And I promise it will be a very strange integrable QFT in 2 dimensions. So the plan now is to study the 1+1 integrable QFT associated to the nonlinear sigma model of AdS3 cross S3 cross T4 with fermions. And because string theory actually has a gauge redundancy on the worldsheet, you have to fix the gauge in some way. So I will do this in light con gauge. And of this integrable quantum field theory, I want to study one object in particular, which is its factorized S matrix. And that justifies a little bit the choice of light con gauge, because light con gauge gets rid of all the unphysical degrees of freedom for you as much as possible. So when you want to use the S matrix, it's a little bit more convenient in this way. And I don't want to tell you all the details, but I will just tell you what we find, starting from the particles. So this particle sits in irreps, irreducible representations, made of 2 bosons and 2 fermions. They are a reducible representation of whatever algebra is left over after I fix the gauge. I don't want even to tell you what that is. And these representations are labeled by an integer mu. There are infinitely many such representations, some of which you can think of fundamental constituents, and the other will come out as bound state representations. And the dispersion omega of p, which depends on mu. You can compute it essentially by symmetry arguments, and is exact in the couplings, and it looks something like this. And you see now all the players of this story. The NSNS, or Vesumilovite model parameter, here, K. Mu, which just labels the different representations. And H, which tells you how much Ramon-Ramon flux you have turned on. And immediately, you can make some observations based on this formula. Well, the first thing that you see, and that doesn't take much, is that it's not a relativistic model. Doesn't need to be, because when you fix light con gauge on the worldsheet, you break relativistic invariance on the worldsheet. The second thing is that it has gapped excitations, but it also has gapless excitations, which are the ones with mu equals to 0. You see that then for small p, p goes to 0, sine p goes to 0, and the gap vanishes. So you have this very unique interplay of gapless and gapped representations or excitations. And they're absolutely necessary, and you can even go and show that the gapless guys, they are protected. It's not that they, when you go and compute something, maybe they will lift this gap and get some little mass. They are protected by symmetry arguments, and they're absolutely necessary in order to reproduce some very important features, like the chiral ring of the dual of this theory. That's not something that I want to go into, but the expert can ask me afterwards. So you absolutely need them, and they're not just something to say, well, you know, okay, they look gapless, but let's forget about it. And, yeah? That's exactly my next point. Very good. Very good. The other property is that it simplifies drastically. At h equals 0. So this is a particle that moves with the speed of light, which happens to be k over 2 pi in this model, either to the left or to the right in 1 + 1 dimensions. So this is the whole energy of a whole state made of many such excitations. So that would be the result, for instance, of doing a Bethe ansatz or a TBA. This is the energy of one single excitation. And you can use this, and we have done it, to derive this formula. So this is a formula that you can get from CFT, but you can also get it from integrability. So that's why I decided to, that H is really the full energy of the spectrum, omega is the dispersion of a given state. And it also simplifies somewhat. That goes back to what I was saying to Jules. When it's k that is 0. Meaning that it looks much more like a lattice-like dispersion, which also hints there should be maybe some dual or equivalent lattice description of this model. That's something that unfortunately I don't have much time to discuss. So this is the spectrum. Now let me give you the S matrix. Well, the S matrix breaks down in blocks because you want to break it down into the reducible representations corresponding to the different particles. So I will call it S mu1, mu2 of P1 and P2. It doesn't depend on some rapidity because this theory is non-relativistic, so it's not obvious that you can put it in the inference form. Let me put in a little hat to remind you that it's a matrix. And I want to write it like this. E to the I phi mu1, mu2 of P1, P2 times S hat 0 mu1, mu2, P1, P2, because the last part is fixed by symmetry. So you have whatever leftover symmetries after fixing the gauge. They act linearly on your two-particle state and are enough to fix the matrix part of the S matrix, or each block, up to one overall normalization, which is this gentleman here. Well, it's fixed completely. Does it solve the Yang-Baxter equation? Yes. So the very interesting thing, and that's what I want to tell you about, this work that I've been doing with Sergei Frolov very recently, is to understand this prefactor or dressing factor, which as always in an integrable model contains all the non-trivial structure about bound states and analyticity and cuts and so on and so forth. And once I understand that, and I understand the analytic properties very well, I will be able to compute the spectrum of this model by relatively straightforward techniques of Bethe ansatz, or thermodynamic Bethe ansatz to be more precise. So let me just tell you, just to tell you what happens at h equal to 0, because I can just write it. This thing here, this S, becomes just e to the I phi of P1, P2. Notice that the mu's are not there because it's independent now of the flavor. It's just a general thing. And S0 is the identity. So I promise that in that case, like, the simplification is like staggering. Okay?
Does this S matrix, the last part, does it only visit unitary in the sense of sort of arctic?
So the S matrix has the potential to be, this part here from symmetry has the potential to solve all the constraints that you want to put that are nonlinear, like unitarity and crossing and so on. I'll tell you just in a second. But of course, that will depend crucially on the prefactor. So it will be something proportional. The right-hand side will be proportional to the identity, as it should be, but the proportionality factor will depend on this prefactor.
But only on the prefactor, not on the lesser. So the lesser by itself would be unitary with the
Yeah, I mean, it's possible. Yeah, exactly. Yeah, with some normalization. Yeah. So now we want to find phi, mu1, mu2 for all these various values of mu. And for simplicity, and also because we are in the process of doing the more general case, we've not done it yet, let's do k equals 0 and h greater than 0. So the opposite corner from the very simple one, the one where the model is lattice-like. And as Jules sort of scooped me a little bit, I want to use things like unitarity. Unitarity will tell you something like, well, there is a braiding unitarity, it tells you that phi mu1, mu2 is related to phi mu2, mu1. And then there is physical or generalized unitarity that tells you that phi has to be real in certain places, or it has to conjugate to something, and so on and so forth. I want to use a crossing symmetry. Even if this theory is non-relativistic, it still has the crossing symmetry that you can understand as arising from a property of the homologic of the algebra of this model under particle-to-particle transformation, particle-to-antiparticle transformation. And that will relate phi mu1, mu2 to phi minus mu1, mu2, because particle to antiparticle will flip mu. And of course, this will be in some different analytically continued region, so it's not in the same region of the momenta. Then, of course, I will use whatever discrete symmetries I have. There is a parity, there is time reversal in this model, just by looking at the Lagrangian. I want to use fusion. I told you that some particles, for instance, if I have mu1 and mu2, I can give you a particle with mass mu1 plus mu2. For mu1, either both positive or both negative. So this tells you that if you have two particles with positive mu, you can make bound states. With negative mu, you can make bound states. With positive and negative, there aren't the right poles in this matrix. You cannot make bound states, which tells you in particular that the massless particles, the gapless particles, they are not bound states of heavier particles, which sort of makes sense. And then finally, and that's key here, and I want to comment on this because maybe you're not so used to it from other relativistic integrable models. I want to use, well, I want to use analyticity, of course. Also for the mirror model. So what do I mean the mirror model? I mean that I have a theory which is in finite space, is defined on this cylinder. And in order to do the thermodynamic Bethe ansatz, I want to introduce a model which is actually rotated, where now I'm in infinite volume, but on a periodic circle for tau. And this is a trick, of course, that has been done also in relativistic models, and is how you compute the spectrum of relativistic models in finite volume. But what I want to stress is that because I exchanged sigma and tau, also p and omega, the momentum and the energy, in the new model, let me put tildes for the new model, are exchanged in this way. For a relativistic model, that's absolutely fine, gives you back the same stuff, because you have omega squared is p squared plus u squared. So all of this works fine. Here you find that the new model has a funny dispersion relation, which involves the inverse sinh. So it's a completely different model, but in order to do our TBA magic and to consider especially excited states and their energy by analytic continuation, we need to be able to analytically continue from the original model to this mirror model. That's possible at the level of the symmetry algebra. It's possible at the level of the matrix part of the S matrix, and we are going to demand that it is possible also for the dressing factors. We can get from one model to the other by, if you were a relativistic theory, shifting the rapidity by some I pi over 2 or something like this, morally. Here we don't have rapidity, it's more complicated, but morally that's what we want to do. Okay, so these are all the ingredients that I need, and I now just want to show you the result and comment a bit on it. Are there questions before I do that? So unfortunately, before I write the result, I need to spend 3 minutes telling you what are the good variables to express these results. Precisely because this model is non-relativistic. Yes, sorry.
So how do you explain that some part of the system is integrable and some part that is not integrable?
Which part is not integrable?
I mean, depending on the parameters, right? Some part
All of it is integrable. I should have stressed this. For any values of these two parameters, you have two-parameter family of integrable models. All integrable. Thank you. I should have made it.
where this comes from.
So that's an excellent question, and it's obvious how it happens for an SNS case. But for the generic case, I don't really have a mathematical construction of this integrability. What I see is that I can prove it at the classical level, and at the quantum level, I can bootstrap a factorized S matrix, and I can check against perturbation theory that it seems to reproduce whatever perturbation theory would tell me. But as always with quantum integrability, it's a little bit subtle, right? Even for a simpler model, it's not always straightforward to really prove or understand in a mathematically consistent way the integrability of a quantum field theory in 2 dimensions. So instead of using p and omega, let me introduce 2 variables which I call x plus and x minus. They are constrained variables, like x plus satisfies a constraint where u is some parameter related to the moment and so on. And the constraint depends explicitly on mu over h with an I. And for the other guy, x minus is a similar thing. And in terms of this x plus and x minus, I can write p, or e to the I p, and omega. Up to some prefactor. And this is not particularly important. The thing that is important is that S at 0 is rational when I use this parameter. When I introduce this parameterization, S at 0 becomes a rational function or matrix. So that seems like a good parameterization. The other thing that I have to tell you is where these x's live. And it turns out that the region where you have either physical particles or particles that are the constituents of physical bound states is outside the unit circle for any mu different from 0. So they live in some region of the complex plane, which is outside the unit circle. For mu precisely equal to 0, things become a little bit different, because x plus and x minus are not independent anymore. You see here that they satisfy the same constraint. And they are basically e to the IP over 2, or e to the minus IP over 2. The other thing that happens is that it doesn't really make sense to consider complex momenta, because there are no bound states that involve physical massless particle. So they end up living exactly on the circle in this case for mu equals to 0. So this is one parameterization that is nice. Indulge me a second, there is another one which is very closely related that is also important. And this parameterization is a rapidity that I call gamma plus or minus, and is related to x plus, for instance, gamma plus, as it follows. And the gamma minus again. Is related in this way. And this is not particularly helpful for massive particles, but with this parameterization, for mu equals 0, S at 0 of gamma 1, gamma 2 is S at 0 of gamma 1 minus gamma 2 over 0, meaning it becomes of difference form. So now we have an interplay between massless and massless particles, massive and massless particles, with a piece of the problem that looks like your difference form S matrix. It's not relativistic, still it's true that omega for these massless particles looks nothing like the dispersion of a relativistic model, but still it's a difference form, which is an enormous simplification. And then, based on this, people have looked and proposed different types of building blocks. One that is natural for massive particles, and one that is natural for massless particles. So let me now give you the answer, finally. Absolutely. If you want to send h to 0, you actually should do a scaling limit. So it's a little more subtle than as it immediately appears. I mean, it depends for what purpose, but there is an h to 0 limit which corresponds to something physical in the model, and that requires a scaling limit. So for mu different from 0, the very natural ingredient is the so-called famous Beiser-Teden-Staudacher, BS phase, which is given on the x-plane as a double integral. And I don't want to be super precise with all the bells and whistles, but I want at least to write this integral is on the unit circle. So what are the ingredients here? You see that there are some log gamma functions. That's the sort of stuff that can give you your zetas that you were after. So at least it seems to have the right dynamics in that sense. You see that here, this gamma function can have singularities when this particular combination gives you something like I times some integer, which is exactly the condition that we had there related to the value of mu for the mass. So this actually, you can go and look very closely at it and see that it actually describes singularities that have to do with exchange of bound states and things like that. So this seems like a very nice, very appropriate thing to have for the massless guys, for the massive guys. And then mu equals 0. This gentleman needs no introduction. The sign-Gordon dressing factor solves the crossing equation and the unitarity equation and so on and so forth. Or at least that was the proposal initially. So it looks like you have a very nice, neat story, but it turns out, and that was the work with Sergey and myself, that even if these massive and massless, they don't really talk to each other because there are no bound states of massive and massless. There are no bound states of massive that give you a massless. So they seem to be two sectors of the theory, pretty disconnected. The correct result is not taking these two guys by themselves, but is to say that phi mu1, mu2 is actually given by the BES phase plus a term related to the sign-Gordon phase plus a new contribution where this phi nu, which I work out with my collaborators, is also a function only of gamma. So this is actually very interesting because it's intuitive if you think about it, that it's true if I scatter only massive particles, that seems like a sector, but in the loops, there will be some massless particles running, and they might very well influence the dressing factor. So when you find the matrix part of this matrix, you don't care, of course, which other representation you are including in the theory, whether they are massive or massless. But if you want to construct the dressing factors with the requirement that I told you, and the most important is the fact that you can continue to this mirror model and get an S matrix which is unitary in the mirror model, then you need these three pieces. It's not immediately obvious maybe, but each of these pieces is unitary by itself in the original model. That's because of the choices of these i's and these minus signs. That's well known for the sign-Gordon factor. But once you go to the mirror model, they are not all individually unitary. And you get stuff from the complex conjugate of this guy that cancels against the one of this guy. So that's actually a very interesting construction, I think, in the theory of integrable models. And I wanted to give you a flavor because I find it very rich, very interesting. I think the experts maybe will recognize something interesting here that might relate to some other models. Certainly the appearance of this sign-Gordon factor was intriguing, to say the least. And then I just want to conclude and tell you what are the next steps. The next steps, of course, are generalize this story to the case where you also have a generic H and K, so the whole two-parameter space, which is work in progress. Then, now that we have the model, we understand the analyticity, do the TBA, compute the spectrum, that we have actually done already. So it would be interesting to start computing some states and compare them with other calculations very carefully, and maybe recast the TBA as some Y system or QQ system. In some cases, this has been very successful in similar models. And then more generally, we can ask how to better study this model, compute, for instance, more complicated objects like this pair of pans topology or other things. This would be related to studying form factors for this model. And that's also something that we have begun to do. And then maybe for the mathematical physicists that are not so interested in string theory interpretation or how to use these to address very important questions that are now open in string theory about holography and so on. There is a very interesting mathematical question, I believe, which is once we have the two-parameter picture, we have this structure, we can take the limit to the case in which it becomes chiral and it becomes the Vesomino-Witten model, and we can compare our description in terms of integrability, in terms of a factorized matrix and so on, with the CFT description, which is native to that corner of the parameter space, and use it to maybe try to understand better how to extend the CFT description. There are some attempts in this direction, so-called hybrid formalism and so on, which never really completely paid off. So it could be very interesting as a cross-dissemination to learn how to generalize what works of the CFT, which is a lot in a particular small corner, to the general case where integrability seems to be much more flexible, even if maybe less powerful just because the model is so much more intricate and you cannot really expect to find closed formulae or very simple answers and so on and so forth. Okay, that's all I wanted to tell you. If you have questions, I'm here. Yes?
Yeah, so I think you mentioned that mu has an interpretation in terms of representation theory.
Yes.
So if you go to h equals 0, you get this
Yeah.
So I am less familiar with this.
Mm-hmm.
So what is the interpretation of mu equals 0?
So mu has actually a very simple geometric interpretation because it is related to the fields that come from the T4 and their supersymmetric partners. Essentially, because the T4 is a flat space, there is a shift invariance there, and you cannot write a term of the form mu squared x squared perturbatively. And that's why you have this mu. So in the Vesomino-Witten model, they are not actually fields from the model, because I cheated a little bit. The full theory is the Vesomino-Witten model plus a conformal field theory on T4. So these guys are related to the conformal field theory of T4 for the bosons. For the fermions, it's actually pretty intricate because it's the usual story when you go from RNS to Green-Schwarz string. You have to use these abstruse identities, as it is called, to map one construction to the other. So the map between the fermions is one-to-one, but it's less transparent, as always when you change from worldsheet supersymmetry to target space supersymmetry. Yes. Yeah. So maybe if for everybody else, what Gaberdiel and Gopakumar have been doing, also together in part with Lawrence Eberhard, in the case of AdS3, was to study this setup at h equal to 0 and k, first of all, generic, and then very specifically the case of k equal 1. Now, k equal 1 is super special because not only the theory is simple, but it's actually free in a very specific sense. It's equivalent to a free conformal field theory, to the symmetric product orbifold of some free fields. And that's also something that you can reproduce by integrability. The thing that's a bit tricky in the Gaberdiel-Gopakumar story is how to deform away from these. So I'm actually working with Matthias and with my former student, Andrea Day, with whom I did some of this work, especially on the CFT side of things, in order to try to understand how you could deform their story. We're actually trying to do this in the case of n=4 super-Yang-Mills, where they also have a proposal for essentially the description of the free Yang-Mills theory as a CFT. And there are many subtleties. I mean, some things are very promising, but some things are very tough just because the model becomes so much. I mean, as we know very well, when you go from free Yang-Mills theory to interacting Yang-Mills theory, it's a world of difference. So that's sort of, yeah. Which one? The last one? This one. This tells us that the scattering of massive particles secretly knows about the existence of massless particles and vice versa. And it tells you that if you tried to invent a model. You say, well, I bootstrapped an S matrix that has only, it has the massive particles. Then you say, you immediately see, I have to put their bound states, otherwise the whole thing falls apart. But say, okay, you do it. But I don't put the massless. I don't have to, they are not generated in scattering. It's some model. Well, you get something incredibly different. So in particular, there has been some work on constructing a so-called quantum spectral curve by looking only at the massive sector. And you construct something, it's absolutely unclear what it is, and in particular, it's not a string theory because it doesn't, I mean, I shouldn't say it's not a string theory, but it's not something where you would have this interpretation of a mirror model. So it's extremely subtle. Of course, you can always bootstrap some integrable models, but then if you want to interpret them, it's an extremely subtle question.